South ogamba otya ssebo?
Mukama wange gye ndi ssebo.
Birungi oba gy'oli oli bulungi?
Ndi bulungi ssebo.
Ekyo kyagabi.
Yeah man. Abatuuze bakyanywa caayi.
Atuuze alabika bakyateekinga breakfast.
Yeah, naluddemu mu lesson esooka. Ndowooza that's
Eh,
why.
Yabawo Bakita. Bakita omaze okunywa tea? Are you done taking tea?
I am done.
Okay. Okay. Think we wait for these ones for around 5 minutes. Then we start.
I think it's time for starting. You can start. Let me remove the sound.
Okay. Okay, very good morning, members. Let me hope we are all doing well. Everything is moving on smoothly. And let me hope we are all learning something new each and every day. Otherwise, we don't need to waste a lot of our time here. Okay, so I think we can start. All the members are right here. Okay, so today we are looking at carbonyl compounds as another homologous series. We had talked about a number of homologous series right from I think senior 5, term 1. So and I think if you are to go back to school, we will complete our alcohols, the remaining bit of it, and then we'll look at carbonyl compounds. So that means those who are going to attend this session and other proceeding sessions of carbonyl compounds, by the time we'll be covering such a homologous series, you will be in a position to understand these things with a lot of ease. So you won't be struggling when you're at school because the things we are going to pass through them. So just make sure you understand them, you give them a lot of time, and you get to understand how these things flow. But as I told you that carbonyl compounds, these ones, their reactions, or some of their reactions, they are kind of similar to those in alcohols and even to those in alkyl halides. As we have been seeing that there are some reactions in alcohols, there are some reactions in alkyl halides, which we saw, which were busy generating carbonyl compounds, or where we are using carbonyl compound to generate such compounds of those homologous series. So we are going to find such reactions or preparation methods even in carbonyl compounds. So there are some going to see that some we have already seen them, even their mechanisms, so they won't give you a hard time. Just that you have to understand what carbonyl compounds are, how do they deviate from other homologous series, which special features have they got, and other concepts. But as I told you when I was teaching, I told you we basically concentrate on four things. When we are reading our concepts, make sure at least when you are handling a given homologous series, you know the isomerism in those homologous series. Make sure you can easily write different isomers of different compounds of that, which are under those homologous series or that homologous series. You can easily name based on the IUPAC name. So, and make sure at least you can write down different preparation methods of compounds of that homologous series. If you are in carbonyl compounds, at least make sure you know 5 preparation methods and you can write down their reaction. So those preparation methods down, you can write down the equations down with the correct reagents, correct conditions, so and correct products. So make sure at least you know those preparation methods. And still, I told you that as you are handling any given homologous series, make sure you know or you can easily write down the reactions of those compounds in that homologous series. When talk about the reactions, that's why you're going to bring in even the mechanisms. After writing down a given reaction, let me say a carbonyl compound with a given reagent to form a given product, you have to be knowing at least the mechanism which is accompanying that such kind of reaction. So majorly, you shouldn't revise the homologous series and you forget to revise the so-called isomerism, the preparation methods, the reactions, and even mastering the mechanisms under that given homologous series. Otherwise, so we are looking at carbonyl compounds. We need to know what are carbonyl compounds, how do they look like in the form of their formula, and like how best can we write them down. And how best can we write them down. Okay, so right here, we are looking at carbonyl compounds as organic compounds which have got a carbonyl carbon. A carbonyl carbon is a functional group which we talked about. It's a functional group which we talked about when we are still writing down our introduction part of organic. And we said that the homologous series, which we call carbonyl compounds, they have got a functional group which is called the carbonyl group. So a carbonyl group has got a carbon atom and a double bond attached to oxygen atom. So whichever compound you are going to find, and that compound is having a carbonyl group, that compound is a carbonyl compound. How a carbonyl group looks like this one, the way you see this carbon here, as we have put it here, because we have said carbonyl compounds, organic compounds with a carbonyl functional group. So it's a carbon and a double bond attached to oxygen. So that carbonyl group, it's a functional group for all carbonyl compounds. So whichever carbonyl compound you are going to find is going to be having such a group. And the reason why you call it a carbonyl compound, it's just because of that functional group. That one should be in your mind, that carbonyl groups look like this. It's a carbon with the oxygen attached. So that's what we call a carbonyl group. It is only one oxygen atom attached to a carbon atom. So, but these carbonyl compounds, sometimes we divide them into two classes. The way we have been dividing alcohols into classes, for example, primary alcohols, secondary alcohols, tertiary alcohols, even carbonyl compounds are divided into classes. The classes of carbonyl compounds are two, that is aldehydes and ketones. So aldehydes and ketones, they are carbonyl compounds, but they are of different classes. So we have got a class of aldehydes and we have got a class of ketones. So those are the two classes in carbonyl compounds. How do aldehydes differ from ketones? Now, the carbonyl compounds, that's the ketones and aldehydes, they both have the carbonyl group because they are carbonyl compounds. But they differ in a way that the aldehydes, for them, they have got a hydrogen atom attached to a carbonyl carbon. But ketones, for them, they lack a hydrogen atom attached to a carbonyl carbon. When you come down here, where we have these two structures, we have the first one, which is an aldehyde. The second one is a ketone. Why are we calling the first one an aldehyde? Because when you look at this aldehyde here, or at this compound here, which we are calling the aldehyde, it has got a hydrogen atom attached to a carbon, which is carrying the oxygen atom. In fact, in this compound, there is a hydrogen atom attached to a carbonyl atom. This is to a carbonyl carbon. This carbonyl group has got a carbonyl carbon, and it's on that carbonyl carbon where hydrogen is attached. Now, we are right here, and we are saying that the ketones, for them, they don't have. Jerry, please mute your video. Jerry, is it Jerry what? Mute your video, please. Remove your video. Okay, thank you. So we are saying right here that aldehydes, for them, they have a hydrogen atom attached to a carbonyl carbon. Ketones, they lack a hydrogen atom attached to a carbonyl carbon. So when you even see this structure of the ketone, the RR groups, those indicate either alkyl groups or aryl groups. For example, this R can be CH3, CH2, this R can be CH3, this R can be a benzene ring, but they are not hydrogen atoms. These R's, they are not hydrogen atoms. They are just alkyl groups or aryl groups. When I talk about of alkyl groups, you understand me. Alkyl groups, those are the CH3, CH2, CH3, CH3, CH2, CH2, those groups. When I talk about of the aryl, I mean the other benzene rings and the cycle rings. But right here, the aryl group we are having, so these aryl groups, they are not meaning hydrogen atoms, but they instead mean alkyl groups or aryl groups. So, but in aldehydes, we only have one alkyl group or aryl group. Then we have a hydrogen atom attached to a carbonyl carbon. So whichever carbonyl compound you see, and that carbonyl compound is having a hydrogen attached to a carbonyl carbon, that means that compound is a carbonyl compound, but under aldehydes. Then when you see any carbonyl compound with a carbonyl carbon, which is not attached to hydrogen atoms or to any hydrogen atom, that compound is a ketone. It's a carbonyl compound under the class of ketones. So that's how we can differentiate ketones from aldehydes. The aldehydes, they have a hydrogen attached to the carbonyl carbon. The ketones, for them, they lack a hydrogen attached to the carbonyl carbon. Now, and there are some tests which we basically perform in lab to distinguish these two classes, the ketones from aldehydes. Those tests are there. We can use oxidizing agents like acidified potassium permanganate. We can use ammoniacal silver nitrate solution. We can use the Fehling's solution. We can use the acidified potassium dichromate. So we can use any other oxidizing agent to distinguish these two. But we'll look at those tests later. Now, after understanding how ketones differ from aldehydes, or how aldehydes look like and how ketones look like, we are going to see that these ketones are basically, or aldehydes, their formula is basically CnH2NO. So if you want to get the formula for ketones, for aldehydes, we use that CnH2NO. But if you want to get that is for ketones and aldehydes. But if you want to get cyclic ketones, that one is going to be reduced by 2 hydrogen atoms. That's CnH2n minus 2O. But if it is just aldehydes or ketones, it is CnH2NO. So those formulas, you have them still. We talked about them at first. Now, we are going direct to nomenclature. We need to know how we can name these compounds. I know we have been naming them. We have been naming these compounds. So, but still we are going to rename them again. So here it is going to be an interactive. We are going to be naming. I'm going to be naming as we are naming. So the first one, the one with the, now when you look at this compound, it has one carbon atom. Of course, this is an aldehyde. So what we are having only here, they are aldehydes. So that's what we have just put there. So now the first aldehyde, this one, odd aldehyde with one carbon atom. You know, when we are naming aldehydes, we end with the suffix al. When we are naming the ketones, we end with the suffix one. So now here we are naming the aldehydes. That means we are going to end with the suffix al. For example, an alkene with one carbon atom is called methane. But because we are having a carbonyl group here, we are going to call this one methanol instead of methane. So that means an alkene with one carbon atom is called methane. But because this compound is having a carbonyl group and it is an aldehyde, therefore it is called methanol. We are going to remove the other suffix of alkanes ne, then we introduce ne, then we introduce. In fact, we are going to remove e, the other suffix e on alkanes. Then we introduce a suffix al. So our compound will become methanol from methane, methanol. Then the one an alkane with 2 carbon atoms is called ethane. Ethane. So we are removing the suffix e to make our compound an aldehyde because there is a carbonyl group. So this one, the second one, we are calling it ethanol from ethane. So we are removing the suffix e and we are introducing al because we are dealing with an aldehyde. So it is becoming ethanol from ethane as the mother alkane. The one with the 3 carbon atoms, an alkane with the 3 carbon atoms, we call it what? Propane. So because this is a carbonyl compound, which is an aldehyde, so instead of calling it propane, we are going to call it propanol. So this one is going to be propanol. We are removing the suffix e on the mother alkane and we replace it with the suffix al to become propanol. When we go to the one with the carbon atom 4, an alkane with the carbon atom 4, we call it what? Butane. So we are removing the suffix e, and therefore our aldehyde becomes butanol. So hope you see how we basically name that. However much, now that is the general naming, but they are going to give you compounds with some substituents attached, some groups attached, where you have to identify the locant numbers. Now, this one, the next one from butanol, this one, it has a general name or it has a special name, which is benzaldehyde. This is an aromatic compound. So benzaldehyde, that one is we have been using it in preparation of many compounds, carboxylic acids, preparation of alcohols, preparation of benzene, and others. Anyway, but this one is called benzene aldehyde. That one has a special name. Then this one is called what? This one, when read the group. Now, in this compound here, remember we said if you have more than 2 carbon atoms, like if a compound attached to benzene is having more than 1 carbon atom, we name that benzene ring as we name that benzene ring as a group, which is phenyl, or we read it as a group. So it becomes a substituent in that case. So now here we cannot say that this one is benzene ethanol. No, that one doesn't work. However much this group is ethanol, this one we cannot name it as benzene. Because this one is going to be ethanol, then this one becomes the substituent or becomes the group. This benzene ring is going to become a group. So therefore, we are going to name it as phenylethanol. So which means that the phenyl group here, the phenyl group is attached onto this carbon atom of ethanol. Of course, because this is the functional group, of course, this one is going to become carbon atom 1. That's why we are calling it phenyl ethanol. Now look at this one down here. It has a methyl group on carbon atom what? Carbon atom 2. So because if you have to count you are counting right from where there is the functional group. So right here you have carbon atom 1, carbon atom 2. So therefore this one is going to become what? 2-methyl-propanol. So you read the locant number of the side group. So the side group is a methyl group, but where is it attached? It's attached on carbon atom 2 of propanol. That's why we are calling it 2-methyl-propanol. 2-methyl-propanol. So now, after looking at this 2-methyl-propanol, we have another compound right here. This one, when you look at this group here, CH3CH, so the naming is going to be based on the rules which we covered. If you guys you remember the rules we talked about of naming these organic compounds, the rules are going to be the same. We are following those same rules. So here you have how many groups attached. So what you have to do, we said in our first rule, we identify the longest continuous chain. Of course, the longest continuous chain we are identifying here should be having the functional group of the aldehydes. So right here, we're going to have 1 carbon, 2, 3, 4. Then if you are to count from this side, it will be 1, 2, 3, 4. So if you are to, now we are counting right from where there is the functional group. So because the functional group is supposed to take the position 1 right here, the one of the carbonyl. So we are seeing 1, 2, 3, 4. Then if you are to consider this side, 1, 2, 3, 4. So now that means we have 2 groups attached. We have a bromide atom attached, or bromide group, and we still have a methyl group attached. But where are they attached? The bromide atom is attached to carbon atom 2, because we are counting as we are moving from where there is the functional group of aldehydes, because we are supposed to give the aldehyde group position 1, since it is the owner of this compound. It's the superior group in this compound, so it's supposed to take the name of the compound, and therefore the functional group of it is supposed to be at position 1. So whatever you are doing, make sure the carbonyl group is at position 1 here. So we are now taking this as 1, 2. So the bromide atom is at position. The methyl group is at position 3. So those who were counting from this side that 1, the methyl group is at position 2, that is wrong. Because when you say that the methyl group is at position 2, then it means the bromide is at 3 and your functional group is taking a position 4, which is very wrong. So we are counting from where there is the functional group, which is the carbonyl group. So that means our bromide is at position 2, our methyl group is at position 3. So that will mean the mother alkane is having 4 carbon atoms. And of course, the carbonyl compound with the 4 carbon atoms is called butanol. So that means we are going to say 2-bromo 3-methyl-butanol, because the 4 carbon atoms here, they are corresponding to butane as the mother alkane, which makes our carbonyl compound to become butanol. Okay. Now, after looking at that, then we have another compound down here. Benzene is carrying a methyl group and is carrying a carbonyl group. Of course, we are still following the rule. This group here is called benzaldehyde, but the methyl group attached is at which position of benzene? So we are giving this carbonyl group position 1. So if the carbonyl group is at position 1, then the methyl group is at which position? We are having position 2 here, 3, 4. So our methyl group is at position 4 because we are giving the carbonyl group position 1 since it is supposed to own this compound. So that means the name is going to become 4-methylbenzaldehyde. The reason why you have brought benzaldehyde because here we have only one carbon. This group here is having only one carbon atom. So we are going to name bringing in the word benzene or benzaldehyde instead of saying methanol. Because someone would say, teacher, can't we say 4? By that it can't even come out. So this group is just benzaldehyde, as we talked about it here. So when we add a group on that benzene, that one also becomes a side group. So therefore we have to give a locant number to the side group as 4 because our carbonyl group, we have maintained it at position 1. So if it is at position 1, then it means this methyl group is at position 4. Therefore, the compound becomes, that is 4-methylbenzaldehyde. So these other compounds are also here. We have this one, which is having a nitro group. This one is also at position 4, that is 4-nitrobenzaldehyde. This hydroxyl group is at position 2, therefore that is 2-hydroxybenzaldehyde. So you can see how easy these guys can be named. So this is 2-hydroxybenzaldehyde, this is 2-nitrobenzaldehyde. So the nomenclature for alkanes, for aldehydes, is in that way. When you are naming an aldehyde which has 2 functional groups, which has 2 groups attached or any other group attached, make sure you identify the locant numbers. But you identify the locant numbers while giving the functional group of aldehydes of ketones position 1. Of aldehydes position 1. So that's how we do it. So in the isomers we are going to be creating, you should be able to name or to give names to those isomers of aldehydes of those carbonyl compounds you are going to write. So you make sure you can easily name them. So you shouldn't get it hard when it comes to nomenclature of aldehydes. Now let's go to the nomenclature of ketones. Unless there is a question there. Okay, so let's go to nomenclature of ketones. For the nomenclature of ketones, we have the first ketone, which is propanone. Now, this one we said for the case of ketones, we name them by replacing the suffix E of the mother with the suffix ONE. Where we have been with the E as the suffix in an alkane, that is like propane, because the first ketone is of course of 3 carbon. We cannot have a ketone of 1 carbon atom. We cannot have a ketone of 2 carbon atoms. So the first ketone is of 3 carbon atoms. But for the case of aldehydes, we have an aldehyde of 1 carbon atom. We have an aldehyde of 2 carbon atoms. But for the case of ketones, it is strictly ketones. They start with 3 carbon atoms. You'll never find a ketone with 1 carbon atom. You never find a ketone with 2 carbon atoms. So the ketone, the lowest ketone you can find, has 3 carbon atoms. And that ketone is propanone. Why we call it propanone? Because 3 carbon atoms, a mother alkane with 3 carbon atoms, we call it propane. Since a mother alkane with 3 carbon atoms, we call it propane, that means we are going to replace the suffix E with the ON to become propanone or to become propanone. So just need to know that here I'm removing the suffix E, I'm adding suffix AL. Here I'm removing suffix E, I'm adding suffix I'm replacing it with the suffix ONE. So such that you come up with the ketones, you come up with aldehydes. Now the first one we said is called the propanone, as you can see it there. So the reason why we are calling this a ketone, because the carbonyl group, the way you see it there, it is not attached to any hydrogen atom. If you are seeing any hydrogen atom attached to a carbonyl group there, that is not a ketone. So this one is a ketone. Why? Because the carbonyl group or the carbonyl carbon is not attached to any hydrogen atom, but it is instead attached to alkyl groups, which are the methyl groups here. Now, because you have a methyl group here, you have also got another methyl group here. So you can also see that right there we have a ketone, since in this compound we have only carbonyl, so we have only the carbonyl carbon carrying the methyl groups, not hydrogen atom. Look at the second one. What's the name? Butanone. So this is called the butanone. This side there is an alkyl group which is an ethyl group. This side there is an alkyl group which is methyl group. So that is called what? Butanone. So the carbonyl group is not attached, or the carbonyl atom carbon is not attached to any hydrogen atom. And because of that, that one is a ketone. Since the carbonyl carbon is not carrying any hydrogen atom, but it is instead carrying alkyl groups. Right here, the alkyl groups, we have ethyl and methyl. So therefore, that one is a ketone, which is called butanone. Why do we call it butanone? Because it has got 4 carbon atoms, and a mother alkane with the 4 carbon atoms is called butane. So when you remove the suffix E and you replace it with ONE, it becomes butanone. So look at the second one. So the third one, what is the name? Should we call it pentanone? Now this one, we are calling it pentane 2-on. Then this one is called the pentane 3-on. Why do you think for butanone you have not called it butane 2-on? Who can give me a reason? Why didn't we say that it is butane 2-on? Oh, why do you think that the third one here, why are we calling it pentane 2-on? Why are we not calling it pentanone? Yes? Is there anyone who can give me the reason there? Why do you think this one we are calling it pentane 3-on? You can easily see that we have just changed the position of the functional group. You remember we talked about over functional isomerism. When the position of the functional group change, even the position, of course, we are going to change its locant number. In this compound here, the carbonyl carbon is at position 2, or the carbonyl group is at position 2. You count the lowest from this side, 1, 2. So that is pentanone. Pentane 2-on. You count from this side for the fourth one. The fourth one, the carbonyl carbon is at 3. The carbonyl group is at 3. Is at position 3 of pentanone of the mother alkane pentane. So that means we are having our ketose group at position 3. That is CH3, CH2CO, that is position 3. Even when we are counting from this side, it is CH3, CH2CO, position 3. So that means this group here it is at position 3, but here it is at position 2. So the two compounds are different. They are isomers. So this is pentane 2-on, this is pentane 3-on. The way we have been looking at alkenes, and we say this is buty 2-in, this is butylphenidine. So, or this is pent2-ene, this is pentylphenidine. It is the same thing here. We have just changed the position of the functional group from position 2 to position 3. When you put it at position 1, then it means that one is no longer a ketone, it's an aldehyde. Because the moment you bring the functional group at position 1, then that is an aldehyde, it is no longer a ketone. Okay. So look at the fourth one and the fifth one. The fifth one is CH3, CH, CO, CH3 with a methyl group. Of course, we identified the longest continuous chain. The longest continuous chain is having how many carbon atoms? 1, 2, 3, 4. The mother alkane with the 4 carbon atoms is called butane. But because the carbonyl group here is not attached to any hydrogen atom, therefore it is becoming butanone. But this butanone is having a side group, which is a methyl group, attached to each carbon atom. So we are counting from where there is this lowest number. So we are going to give it position 3, not 2. Not 2, because the challenge is going to come when you say 2-methyl instead of 3-methyl. Because we are counting from where there is the lowest number of the functional group. Where are we having the lowest number of the functional group? It is this side, where we have our carbonyl group at position 2. So if our carbonyl group is at position 2, then it means this methyl group is at position 3. So you cannot say the carbonyl group is at position 2, then the functional group is also at position 2. You are lying. So you first identify the position of the functional group, that this one is at position 2. So you count as you are going behind. So therefore, this one is at position 3 or 2 or what? So since this one is at position 2, then the methyl group is attached at carbon atom of 3, not 2. That's why our compound is becoming 3-methyl-butanone. Or someone can say 3-methyl-butane-2-one, which is okay. Because all ketones, the functional group is at position 2. So this one can be called butane-2-one. This one can be called the buta-2-butane-2-one. So because for all ketones, the position, the lowest position their functional group can get is 2. If you put it at 1, that becomes aldehyde. Anyway, then this one, it's a ring. So we label it, or we call it cyclo. But because of its shape, there are 6 carbon atoms. Therefore, it becomes cyclohexane. But because there is this group here for the ketone, therefore it becomes cyclohexanone. So now, in some sense, they tell you synthesize cyclohexanone from cyclohexene. Now you'll find someone who cannot write cyclohexanone. So you have to know cyclohexanone looks like how there is a cyclo ring with 6 carbon atoms, but because it is hexanone, there is a ketose group, or there is a carbonyl group which is not attached to any hydrogen atom. So it is a ketone. So that is a cyclohexanone. Then this one is called what? Cyclobutanone, as you can see it there. So we have this one. So from cyclobutanone, we have phenylethanone. We said if there are 2 carbon atoms attached to benzene, that benzene ring becomes a group or becomes a side group. So that's why we are saying phenyl. Instead of benzene, small benzene what? So it becomes a group because what is attached has 2 carbon atoms or has more than 1 carbon atom. So for it will take the name. So this one is going to be ethanone. Then this one is going to become a group, which is phenyl. So that means this compound is becoming phenylethanone. Now, then the second one, this is phenylpropanone. Now we have this one. So there are two groups attached onto this carbon or carbonyl group. So therefore, this one is a ketone, which is called diphenylmethanone. So that one is the only one which you can call methanone. It's the only one we can call methanone. So that is diphenylmethanone. But in real sense, we don't have methanone separate. You never find methanone there that we have the way we have butanone that you are going to find in methanone. No. You can only call this one methanone if at all there are some other groups attached, the way you see here. So these are two phenyl groups attached. That's why you're calling them diphenyl. Here you have only one carbon atom, therefore it becomes the methanol. So it is diphenylmethanone. Okay, so that's how best we can name ketones. So wherever you are going to find the ketones, you should be in a position to name each and every ketone, to name each and every aldehyde. So, okay, so now what I'm going to do, I'm going to give you the names, and you write for me the formulas. I'm going to give you the names, you write for me the formulas of these compounds. So I'm very sure you have where to write. To get where to write, you are going to screen share your work. We look at those formulas of yours. So I'm going to give you the name. So for you, write the formula. Okay, the first one, you are going to write for me cyclopropanone. Why are you accessing it from there? You mean you don't have the app for Zoom? You are lying, you are lying. Cyclopropanone, that's the first one. You write cyclopropanone, then you write the formula. Make sure I write the formula there. That's the name. Another one. Another one. Think it's going to be. So this one was phenylpropanone. Anyway, so we are going to write the formula of this one is supposed to be phenyl. Okay. Search for that one, I think. Okay. Then we are going to write phenyl. Phenylpropanol. So you write its formula, phenylpropanol. Then the third one, you write search. We are going to write 2 bromophenyl ethanol. So you write 2-bromo phenyl ethanol. 2-bromophenyl ethanol. Then the fourth one, the fourth one, the fourth one, and the fourth one you're going to write 3-hydroxy butanol, and the last one, the fifth one. The fourth one I said is 3-hydroxybutanol. That's the fourth one. The fifth one, you are going to write I think the last one you're going to write 2-bromo 4-hydroxy so you're going to write 2-bromo 4-hydroxy hexane 2 on hexane 3 on hexane 2 sorry hexane 3 on. The name is 2-bromo 4-hydroxy hexane 3 on. So those are the 5 one. Let me type them here. I said the first one is cyclopropanone. The first one. Cyclopropanone. That's the first one, cyclopropanone. The second one. Second one I said phenylpropanol. Phenylpropanol. Then the third one, 2-bromophenylethanone. 2-bromophenylethanone. And fourth one, the fourth one is 3-hydroxybutanone. 3-hydroxybutanone. Then the fifth one is 2-bromo. Then 4-hydroxy. Hexane. Perion. 2-bromo, 4-hydroxyhexane. Yeah. So those are the 5 ones. 2-bromo, 4-hydroxyhexane, 3-hydroxybutanone, 2-bromophenylethanone, and the phenylpropanol. So please write the structures down, and then we look at what you have written before we go to isomers. Please be very fast. If you are done, you kindly share and you look at and you comment on your answers. Is there anyone who is done to share? Yes, show is done.
Teacher,
Yes.
sorry, I was having problems with my network, but I'm done.
Okay, if you are done, you can screen share your structures or your formulas.
Teacher, are you seeing my work?
Not really, you haven't shared.
But I've shared.
Sure?
Yes.
I'm seeing it.
You are seeing it, yeah? Let me see. Okay. Yeah, I'm seeing it now. Cyclopropanone. Please zoom it a little bit. Okay, cyclopropanone. Okay, that is okay. That is fine. Phenylopropanol. CH2, CH2, CHO. Okay. 2-bromophenylethanol. 2-bromo. then phenylethanol. Never much write your benzene rings very well, because this ring is not correct, and this one, the way you're writing your benzene rings, that was not accepted. Yes.
Yes.
Make sure that ring inside is like equal on both on all sides. But you see this side there is a lot of space. It is moved this side. So that ring inside, make sure it is like it is leaving the same space. So it should be in the middle.
Yes, teacher.
Then hydroxybutanone. Hydroxybutanone. Okay. 1, 2, 3. 1, 2, 3. Okay. Hydroxybutanone. Then 2-bromo for hydroxyhexanthreone. Where is your bromide group on this compound? I'm not seeing any bromide atom. Yet we are seeing 2-bromo for hydroxy.
So let me redo that. I didn't read the thing clear.
Okay. But thank you for the other. The others are somehow correct. They are correct, in fact. Just that the formulas are down, which are supposed to be revised. Catherine, cyclopropanone. Yeah, that's okay. Phenyloprop. Zoom it a little bit. Zoom a little bit. Now, your phenylopropanol is not correct. I don't know whether I'm the only thing wrong, but there are some excess hydrogen atoms you have indicated on that compound. This is benzene. So from benzene, that carbon atom right from benzene, it is having 3 carbon atoms, yet it's supposed to have 2. So it is having excess bonds. Hope you have seen it in Abuja. Abuja, are you there? Catherine, we can't hear you, please. Okay. Someone else share the work, want to go to another concept? I just want to look at least for the first 3 members. Now, we have removed your work. Okay. The first one, that's cyclopropanone. That is okay. Phenylpropanol. Okay, that one is also okay. 2-bromophenylethanone. Okay, 2-bromophenylethanone. But wait, 2-bromophenylethanone. This structure. If you have to call it 2-bromophenylethanone. Let's wait a little bit. Because if anyway, okay, it is okay. Then hydroxybutanone. Hydroxybutanone. Okay. 1, 2, 3. Okay. Then this one, 2-bromo for hydroxy, hexane 3 on. 2-bromo. That's one. 2-bromo, then for hydroxy. Okay. Okay. Yeah, that's okay. So thank you, Maki. Your work is fine. Okay, something remaining with unknown member, such that we go to isomerism. So I told you, make sure you can name these compounds, because the challenge will come when you are told to synthesize something you can't even write, or when you are even told to synthesize it in words without using equations. You have to know the nomenclature. So nomenclature is a very big part of any homologous series. So if you don't understand how to name this compound, it becomes very tricky for you. Any other member to share the work?
Then I am not done.
The first one, phenylopropanol. Okay, that is okay. Cyclopropanol. Okay, cyclopropanol. It's fine, that is also fine. Then go down to bromophenylethanone. To bromophenylethanone. Okay. But this 2-bromophenyl ethanol, anyway, but I'm going to comment about it because it seems that structure, there is another structure supposed to form. Because if you have named the phenyl as a group, then a phenyl cannot have a position still. And I think this compound, which we have written right here, first wait, because if this is Br on 2 benzene, that's 2-bromo. Of course, this is ethanol. Bromo. Okay. But we have another structure which may have, I think, the same reasoning. I'll talk about it later. So scroll down. Hydroxybutanone. CH3CH, okay. 1, 2,
I'm
3.
not done with the last one.
It's okay, it is fine. Try out. We can now go to, I think, isomerism. For the physical properties, I think that when we talk about only the boiling points, and I think maybe the boiling point. So physical properties, of course, carbonyl compound, they have got higher boiling points than alcohols and than alkanes. So carbonyl compound, they have higher boiling points. Why? It's just because they have got, when you look at them, the first thing they have got is that they can form what we call hydrogen bonds because they have got a polar bond. Since they have that carbonyl group, which carbonyl group has an oxygen atom, they can easily form what we call a polar bond or dipole moments. Because they can form dipole moments, then they can form what you call intermolecular hydrogen bonds. So those intermolecular hydrogen bonds which are created together with the covalent bonds they have in their carbon-hydrogen bonds and the carbon-carbon bonds make them to have higher boiling points than the corresponding alcohols and the alkanes of the same molecular mass. So therefore, carbonyl compounds and ketones, or that aldehydes and ketones, because they are polar compounds, they have got higher boiling points than other non-polar compounds like alkanes. For example, propanol has a higher boiling point than butane, yet they have the same molecular mass. So the reason why propanol has a higher molecular mass than butane, so they are has a higher boiling point than butane, yet they have the same molecular mass, is because propanol has a polar carbon-oxygen bond, which we call the carbonyl group. Since it has that polar group, it can easily form intermolecular hydrogen bond or intermolecular hydrogen bonds, which are also hard to break, thus making that compound to have high boiling points. The way we explained the boiling point for alcohols, it is even the same for carbonyl compounds. We are saying the carbonyl compounds, they have higher boiling points. Why? Because they are polar. They have a polar group, which polar group can easily form intermolecular hydrogen bonds with the, so it can easily form intermolecular hydrogen bonds, which are also hard to break, so making them to have higher boiling points than non-polar compounds like alkanes. So we have given an example. When you look at propanol and the butane, they have the same molecular mass. You would expect them to have the same boiling point, but they have different boiling points just because propanol is polar or has a polar bond, yet butane has no polar bond. Therefore, in butane, the atoms are only held by weak van der Waals forces of attraction, which are very easy to break. But in propanol, the atoms are held by the weak van der Waals forces of attraction together with the intermolecular hydrogen bonds. Therefore, for you to break such bonds, the intermolecular hydrogen bonds and the weak van der Waals forces of attraction in propanol, you need a lot of heat than the one you need in butane. So if you are explaining the physical property of boiling point in carbonyl compounds, you should bring in the concept of intermolecular hydrogen bonds, which is as a result of the polar bond in these compounds, in carbonyl compounds, which polar bond can easily form those intermolecular hydrogen bonds, and they are not easy to break, or they require a lot of heat to break. So it is the same thing which we explained in alcohols, if you remember very well, because even alcohols, we say they have got a polar bond. Therefore, they can form dipole moments, which can result into formation of intermolecular hydrogen bonds. Therefore, the molecules of alcohols are held together by weak van der Waals forces of attraction, together with intermolecular hydrogen bonds. Therefore, breaking them will require you to heat at that compound at high temperature than non-polar compounds of the same molecular mass like alkanes. So the explanation is the same as that we made in alcohols. We are going to isomerism. We talked about isomerism in alcohols, isomerism in alkanes, isomerism in alkenes, isomerism in alkyl halides, whatever. And you remember what we talked about when we are defining isomerism. We have two types of isomerism. We have the chain isomerism and the so-called structure isomerism and the stereoisomerism. But we basically have been talking about of the structural isomerism, where we have chain isomerism, positional isomerism, and the functional isomerism. So you know, when you change the position of the functional group, then what you are having is positional isomerism. When you keep on changing the structure of the arrangement of carbon atoms in the chain, that is chain isomerism. When you keep on changing the functional group themselves from alcohol, let me say, to ether group, to what? That is functional isomerism. So you know what functional isomerism is, you know what positional isomerism is, you know what chain isomerism is under structure isomerism. So when you look at carbonyl compounds, you can easily create a number of isomers. You can create structural isomers, you can create chain isomers. Chain isomers, that one you just change the position, the arrangement of carbon atoms in the chain. You say, let me put this one up, let me put one this. So you just change the arrangement of carbon atoms. So you remember that one. We have been changing it in whatever homologous cell we have been handling. We have been writing down in the chain isomerism or the chain isomers. For the case of the position isomerism, that one, for the position isomers, we have been doing it. You change the position of the functional group. For example, because this one they're having a carbonyl group, you keep on shifting it from carbon atom 1, 2, 3, 4, depending on this length of the compound. And whichever position it gets, it becomes an isomer. For example, when we are dealing with the alkenes, we could put the double bond at position 1, it becomes buty, let me say buty 1 in. When you shift it to position 2, it becomes buty 2 in. When you shift it to position 3, it becomes buty 3 in. When you shift it to position 4, it becomes buty 4 in, like that. So that is a position isomerism. We just keep on changing the position taken by the functional group. So when you come to functional isomerism, that one will change the functional group itself. If you have been with the functional group as hydroxyl, we change it to an ether group. So instead of having a compound as an alcohol, it becomes an ether. So that is a functional isomerism. Now, when you look at these carbonyl compounds, we said we have two classes. We have ketones and we have aldehydes. So these guys, they have got, of course, isomers in them, or they can form isomers. Which isomers? They can still form they can form chain isomers. They can form position. They can show position isomerism, and at the same time they can show functional isomerism. So carbonyl compounds can show both three types of structure isomerism. They can show chain isomers or isomerism. They can show position isomerism. They can still show functional isomerism. They are functionally isomeric to ethers. They are functional isomeric to alkenes. They are functional isomeric to alcohols, even enols. Enols, those are alcohols which have got a double bond in them. Okay, so let us look at this one. This first example here. An organic compound 2 contains that and that and that. Determine the empirical formula, the structure formula, vapor density is there. You are going to calculate this down. Then after calculating, you write the isomers of that compound. So for the case of isomers, that one you are going to create them. I'm very sure you have been writing these isomers. You know how we create structure. You know how we create chain isomers. You know how we create position. Position, you just change the functional group position. Because the functional group here for the compound you're going to obtain, I think it's going to be the carbonyl group because we're in carbonyl compounds. So just keep on changing the position of the carbonyl group from position, let me say 2, 3, what, such that if it was a butane 2 on, becomes, let me say, if it was pentane 2 on, becomes pentane 3 on, like that. So that is the position. Chain, you just change the arrangement of carbon atoms in the what? In the chain. But the position of the functional group remain at position 1. That one you should know it. Okay, so I think you should try out this example 1 within these remaining minutes, and you look at your work very fast. Okay, so determine that empirical formula. Then you get the structure formula. Then you write the formula and the name of the possible isomers. Then after you share, so I need to look at the work of each and every individual here. So please do it very fast and then you share the work. You have only 5 minutes or 7 to do that. Yeah, I think our time is done. So I will need to see who is done and present. I've used enough time to write down that number. I'm very sure you have got the empirical formula, the structure formula, and we have created down the possible isomers. So those who are done, please share your work and we comment on it. Anyone who is done, yes, no one is yet done with the empirical formula and the isomers. Please, our time is running off. We should present our work. For those who are done, just scan the work and are you done? Teams members are still writing down the work, but anyway. But I'm very sure the part of the empirical formula, structure formula, that one is very easy. I don't expect anyone to face a challenge there with writing empirical formula and even molecular formula or structure formula. Then isomers, at least we can create a chain, we can create position. Yeah, at least we can create those ones, the chain and the position isomers. It's already 12:46, but I'm not seeing any member who is ready to present. Okay. So anyway, so let me hope we have all tried out this question right here. If you have tried out, I'm very sure you have obtained this kind of empirical formula down here, C4H8O. Then even the molecular formula using vapor density, you get it as still the same formula. So it was very direct. You could easily get it, C4H8. Vapor density, just multiply it by 2, so it becomes 72. You equate it to your empirical formula, you find the N. N is 1, therefore your molecular formula is C4H8O. So that one was very easy. For the case of the isomers, what you have got, it is having only one oxygen atom. And when you look at the hydrogen atoms, it cannot be an alcohol. Because if it was an alcohol, you were not supposed to have 8 hydrogen atoms right here. At least they were supposed to be around, is it 10, something like that, because C4H10O. But right here you have only C4H8O, which means it cannot be an alcohol, but instead either an aldehyde or a ketone. So that's why in the formulas which we have here, we have a ketone of 4 carbon atoms and we have an aldehyde of 4 carbon atoms. That is CH3, CH2, CH2, CHO, butanol. Then we have a ketone of 4, which is butanol. It can be also an isomer. So then we can have a structural isomer here, which is a chain. This is the third one, is a chain isomer. We are just changing the what? We are changing the arrangement of carbon atoms here. Where you have been with the CH3 here, you bring it onto this carbon. So that one becomes 2-methylpropanol. So that one is also an isomer, which is a chain isomer, 2-methylpropanol. You can still create another isomer, which is cyclobutanol, because remember these were 4 carbon atoms. I had 8 hydrogen atoms and 1 oxygen atoms. You can create an alcohol. So this is a functional isomer. So therefore, carbonyl compounds are functionally isomeric to alcohols. So you can see cyclobutanol from such a kind of what? From such a carbonyl compound. Then you have another one, which is 2-methyl cyclopropanol. So this one is also an alcohol. Still it is from carbonyl compound. Therefore, carbonyl compounds are functionally isomeric to alcohols. So then you can have enols. These ones which you are seeing down here, they are called enols. They are compounds which have got a hydroxyl group together with a double bond. So such compounds, they are called enols. They are alcohols, but with a double bond. So alcohols which have got a double bond, they are called enols. So that's why this one is called butyl 2-in-1-ol, or butyl 2-in-1-ol. That's like a butene, then there is ol, or there is an alcohol or hydroxyl group. So this one is called an eno, or it's eno. It's an alcohol which is called eno. So whenever you hear the word enols, those are alcohols with a double bond somewhere. So we can have such an isomer from carbonyl compounds. So that one can be eno, the way it is right there. It can be this kind of eno here, butyl 2-in-1-ol, or it can be butyl 3-in-1-ol, which means the double bond is at position 2. Here, the double bond is at position 3. Other the hydroxyl group are remaining at position 1. So I'm very sure the common isomers you could write, they are these 3 ones here, or the 4 ones. The first one, the second one, the third one, the fourth one. However much these are also isomers, you need to know them. Because in some analysis questions, we can be targeting a given isomer like this one, this beauty 2-in-1-ol. And if you don't know that this can be also an isomer from here, it means for you are going to write only the first 4, then you think they are done. Yet there are other isomers, and we are targeting only one isomer from those ones. So you should be able to write all the possible isomers. You should be in know that carbonyl compounds, they are function isomeric to alcohols, to enols, and to ethers. Because even this one is ether. When you look at this one with a double bond, ethoxyethene, are you seeing it right here? So you need to know how to come up with all those isomers. Otherwise, carbonyl compounds, I think they are the compounds with the highest number of isomers. So the moment you get a carbonyl compound, you should be in a position to write all the isomers which are possible from there. So isomeric to ethers, isomeric to ethers, isomeric to alcohols, isomeric to enols. So you should be in the know of that. Otherwise, those are some of the isomers you could point out, and you get your scores. Okay. So let me hope you have also obtained the same compound, and you have also written some of the similar isomers there. If you have done so, that's well and good. So tomorrow we are going to look at laboratory preparations of these carbonyl compounds. How best can we prepare them? After understanding the nomenclature and the isomerism of these carbonyl compounds, then we are good to go to preparation methods. Under preparation methods, we will look at some mechanisms which are there. Those which have acceptable mechanism, write them. Those which do not require mechanism, we also look at them. But I'm very sure in some of the preparations, we may not write the mechanism. The mechanism, we will find them more in reactions. However much, we will have some preparation methods which have got mechanisms. So just to prepare, is it tomorrow? Oh man, I think to be Monday. Because I think tomorrow you have biology discussion or biology presentation. So I think we are meeting on Monday with laboratory prep. Anyway, are you guys going to be here next week?
Chano.
Bakita with a very big no. Okay. So
teacher,
yes,
the way you love teaching, even Xmas week you want to teach.
if at all you wish, why not?
Mama teacher, it's Kawa. You can come and teach.
But I'm very sure Bakita can't be here. Bakita, you are going in the village. Or you're already in the village.
I'm going to be around. Don't worry.
Anyway, I'm very sure most of you may not be able to attend because it is a festive week. But as you are there enjoy with the content, yeah? Enjoying with empty head, it is also dangerous. So as you are enjoying, as you are eating meat and what, also eat some content somehow. Anyway, but relax. Yeah. What I can tell you, a festive week, take your time, relax, and enjoy with your family members, such that you come back when you are fresh, when you are ready to learn. Yeah, because I'm very sure these 2 weeks you have been studying. Yeah, enjoy your week, enjoy your festive week. Yeah, so but as you're enjoying, make sure you revise call. You enjoy with the content. Anyway, but relax a little bit, eat, but don't eat a lot. I know some of you with eating, when it comes to meat and chicken, you become great Christians in fishing out those tissues. Anyway, so we are going to stop here. I think when we meet again, we talk about the laboratory preparations of carbonyl compounds, how best we can prepare carbonyl compounds. I don't know when we'll meet again, whether in January or whatever, but when we meet, we'll talk about that. So otherwise, thank you for attending for all these 2 weeks. Thank you for being attentive and participating. So don't relax, still continue revising, even if you are not having lessons or what. Spare some time and go through your books. Strike out some numbers of math, some numbers of chemistry, and some bio numbers. So otherwise, we are going to stop here for today. Thank you for attending. If at all there is anything like a question, you can ask before we leave here. Kenya, you want to start on Christmas? That is not possible. Yeah. Especially Bakita. I'm very sure she'll be there preparing meat for the family members and some chicken stew. Okay, if there is any question or any inquiry, please, it's this time, you do it right now. Otherwise, after here, we are locking ourselves into the weekend and into the festive week. Okay. So if there is no any question, we meet when God wishes. Have a nice time. May God keep you safe as you are also keeping yourselves safe. Yeah, so don't party a lot. Don't eat a lot. Start home. Hey, enjoy with your family members. Don't go outside. Unless when you are going with your family members, but stay safe. Make sure you stay safe. We need you when you are alive, not in parts, but when you are in health. Okay, have a nice time, guys.
Merry Christmas,
Enjoy your
teacher.
festive season. Merry Christmas to you too, guys, and a Happy New Year.
Ticha oluzungu nga walukozeeko.
That is American English.
Oba Rwanda English. First time in
Rwandese, they
Rwanda,
don't know.
I came back speaking English.
Rwandese don't know English. That can't be Rwandese English. Rwandese English.
You never know
Rwandese,
the influence.
they don't know English. So you can't learn anything from them when it comes to English.
Please
Maki,
be.
bye. Yeah.
Bye, teacher.
Bye, guys.